In this section, we will zoom into the UML data model. UML stands for Unified Modeling Language. Important to note is that it is not an object-oriented development methodology, but a language. In other words, it is a notation. It was accepted in 1997 as a standard by the OMG, Object Management Group. This group regularly issues standards and guidelines with respect to object-oriented design. The most recent version is UML 2.0, introduced in 2004. UML includes many types of diagrams, each of which focus on particular parts of the system design. In this section, we will especially focus on database modeling. Hence, we will discuss the class diagram, which is the most important in a database modeling context. Class diagrams allow us to visualize both classes and associations between them. Let's get into more detail. So the class diagram is an object-oriented diagram. Before we start discussing it, let's briefly refresh the basic concepts of object orientation. Note that these are extensively discussed in other courses. In object-oriented system design, two very important concepts are classes and objects. A class corresponds to an entity type, like student. An object is a specific instance of a class. In other words, an object corresponds to an entity. Each object has state and behavior. State refers to the characteristics or attributes of the object. Here you can think of attributes such as name, date of birth, gender, etc. The behavior represents the procedures that can be invoked on an object. For the student object, we can have behaviors such as register for course, or we can have behavior such as is passed, which is a small routine or procedure which allows us to verify whether a student has passed for a particular course, yes or no. So an object has both state and behavior. Generalization and specialization relationships are also possible in object orientation. So we can also have subclasses and superclasses. We can have a superclass person and a subclass student and another subclass professor, for example. Other very important concepts are polymorphism, overloading, and dynamic binding. Polymorphism or overloading means that basically we can use the same method names, the same procedure names in different classes. That means that the same procedure name can hence have a different implementation depending upon the object on which it is invoked. As a very simple example, let's have a look at the operation plus for adding. Actually here, the method signature is plus, but whether we invoke it on floats or integers, the implementation will be different, since the procedure needed to add integers is different than the procedure needed to add floating point numbers. So you can have the same method name, in this case plus, but with a different implementation behind. Let's just give another example of that. Let's say we have a person superclass with three subclasses: bachelor student, master student, and PhD student. Each of these subclasses has a method is passed. However, for PhD students, the method is passed will verify whether the average mark is above 14. For master and bachelor students, the method is passed will verify whether the average mark is above 10. So the method name stays the same, is passed, but the implementation is different. For bachelor and master students, it will verify whether the average mark is above 10, whereas for PhD students, it will verify whether the average mark is above 14. Dynamic binding is a concept which very closely relates to polymorphism and overloading. It means that the exact implementation of the function call depends on the object that receives the function call. Dynamic binding means that if I have a bunch of students, and some of them are bachelor students, some of them are master students, other ones are PhD students, and if I then send the message is passed to these students, then dynamic binding means that at runtime, when the application is being executed, the system will decide which method, which implementation of the isPassed method to invoke. So if it's a master student, the system will invoke the method which verifies whether the mark or average mark is bigger than 10. If it would be a PhD student, the system will verify whether the average mark is above 14. This is dynamic binding, right? And here you can see that also illustrated by means of a printing message. You send a print message, but depending upon the printer you send it to, a different method will be invoked. So the mapping of the method name to the actual implementation is delayed until runtime. This is the key idea of object orientation, or this is dynamic binding. Object-oriented DBMSs allow then to make objects persistent. In other words, if you look at an object-oriented programming language, OOPL, like Java, objects typically only exist during program execution. Objects which only exist during program execution are referred to as transient objects. When the program stops, these objects stop to exist. They are removed from memory and we no longer have access to them. Object-oriented DBMSs will make these objects persistent. Two popular examples of object-oriented DBMSs are Gemstone and ObjectDB. The latter, ObjectDB, is an open source OODBMS, by the way. Obviously, this is strongly dependent upon the programming language. So standards would come in handy here to standardize the way objects can be made persistent. Object-oriented DBMSs have not been very successful in the industry, except for niche applications, for very specific applications, such as scientific applications, for example. They have not been very successful in the industry because they are generally perceived as difficult to handle. Let's now zoom a bit further into the UML class diagram. In the UML class diagram, two key concepts are classes and associations. Classes are what we refer to as entity types in the ER model. Associations are what we refer to as relationship types in the ER model. Entities are called objects. Each object has a unique identity. Each object will typically have a unique identifier. Think of it as a key attribute type or a primary key. An object has both state and behavior. We already mentioned that. The state are the attributes. That means an object's name, for example, or a student's name, for example, a student's gender, a student's email address, etc. The behavior are then the operations that can be invoked on the object. For example, student is passed and student registered for course. Each operation has a signature, interface, and an implementation method. So, if we look at the operation is passed, then the signature is passed, that's the name, and the implementation is then a piece of code that comes with it which verifies whether the student has a mark above 10, let's say. So the implementation actually provides us with how the operation should be conducted. In object-oriented design, it is common to add both selectors and modifiers to object definitions. Selectors and modifiers are also referred to as getters and setters. Selector, or a getter, allows me to get the value for a particular attribute. In other words, it allows me to get the name for a student, or maybe even get the age or gender of a student. A modifier or a setter allows me to set the name of a student, to set the gender of a student. Getters and setters, or selectors or modifiers, are two very important standard routines which are always included in object-oriented system design. A class is then a set of objects with similar characteristics. So you can think of a class student, which is a set of student objects, obviously with similar characteristics. Objects are instances of a class, just as entities are instances of an entity type. An association is a structural link between classes or relationship type. A link is then an instance of an association. In class diagrams, the associations can have all possible multiplicities, all possible cardinalities. Just as it was supported in the ER model, we can have associations with a minimum cardinality of 0, maximum cardinality of n, minimum cardinality of 0, maximum cardinality of 1, minimum cardinality of 1, maximum cardinality of n, minimum cardinality, and maximum cardinality of 1. So all these different cardinalities are perfectly supported in the UML class diagram. Multi-valued attributes are modeled as a separate class. So if we would have a department that has multiple locations, then instead of modeling location as a multi-valued attribute type, it will be modeled as a separate class with an association with department. Multiple associations between classes are possible. Also, just as in the ER model, unary or reflexive associations can also be modeled. A handy feature in UML is that you can also have unidirectional and bidirectional associations. An association can be further annotated according to the way it is going to be used. Unidirectional means that there's only one way or direction of querying objects, indicated with an arrow in the UML diagram. A bidirectional association then allows you to navigate in two possible ways. Obviously, this highly depends upon how the classes will be used. In this particular case, how you will navigate from one class to another. Let's work out some examples. Here you can see an example of a unidirectional association. We have an association between order and customer. In our diagram, order has three attributes: date received, is prepaid, price. It has two methods, dispatch and close. Dispatch and close are the method names, and obviously there's an implementation that comes with it. Then we have a class customer with attributes name, billing address, and credit rating. Here you can see that the association between order and customer is unidirectional. You can see that by means of the arrow received from. An order is received from a customer. So here, by indicating this arrow in our class diagram, we are indicating that we will always navigate from order to customer. An association should not always be unidirectional. It can also be bidirectional. A bidirectional association means that it is possible to navigate in both ways. Here we have a class person and a class magazine. Person has attributes name and address, and it has two modifier or setter methods, change address, change name. Magazine has attributes title and editor, and two modifier or setter methods called change title, change editor. You can also see the cardinalities or multiplicities that come with the association. A person can subscribe to minimum 0, maximum n magazines. A magazine can have minimum 0, maximum n subscribers. Starting from a person object, you can then access the magazines that person object is related to. But here, since it's a bidirectional association, it is also perfectly possible to navigate the other way around. To start from magazine and navigate to person. So when there's no arrow, it is basically indicating that both directions can be followed to access the related objects. Whether you will be using a unidirectional or a bidirectional association highly depends upon the application and what you want to do with your UML class model. Associations can be further annotated by means of qualifiers. A qualifier can be thought of as an index key. Allows us to navigate from one class to another using a particular index key. So here you can see an example. So we have team and player. A team can have a minimum of 0, a maximum of n players. A player is always related to minimum 1, maximum 1 teams. In other words, minimum 1, maximum 1 refers to exactly one team. We can now add a qualifier next to team, and the qualifier is, in this case, is position. A team at a particular position has 0 or 1 players. Position can be forward, can be midfielder, can be defender, for example, if you would be talking about soccer. So the qualifier specifies one or more attributes, in this case it's one attribute, position, which are used as an index key for navigating from the qualified class to the target class. So position is here used as an index key to navigate from the qualified class, which is team, to the target class, which is player. Thanks to the index key, thanks to the qualifier, the multiplicity is reduced in this particular case. These qualified associations come in handy as you will start defining weak entity types. Remember, as we discussed it in the EER model, a weak entity type is an entity type which cannot produce its own key. In other words, it is existent dependent. Remember, in the ER model we said a weak entity type is always existent dependent. The reverse was not true. An existent dependent entity type is not always weak. Well, here we can perfectly model weak entity types using the idea of a qualified association. Remember the example we discussed earlier. Room was a weak entity type which was existent dependent on hotel. Well, here we are going to add room number, which was the partial key, remember, as a qualifier next to the hotel class. So a hotel with a particular room number corresponds to one room. So if you select a particular hotel, combine it with a particular room number, which is the qualifier here, then we will get one room. Okay? So weak entity types can be perfectly represented here using these qualified associations. Obviously, in the object-oriented model, we can also model specializations and generalizations. Remember, specialization is an is-a relationship. A student is a person. That's why it makes sense to define student as a subclass of person. A professor is a person. That's why it makes sense to define professor as a subclass of person. Generalization is bottom-up synthesis. It means that you start from student and professor and generalize to person. Specialization is top-down analysis. It means you start from person and you specialize into student and professor. In generalization, specialization, you have the idea of inheritance. Inheritance means that the subclasses are going to inherit both attributes and associations from the superclass. Just as in the EER model, these specializations can be disjoint or overlap. Disjoint means that an object can only belong to one particular subclass. That's a disjoint specialization, just as we define it in the EER model. An overlap specialization means that an object can belong to multiple subclasses simultaneously. Here you can see an example of inheritance in UML. You can see the subclasses checking account and savings account. Again, remember that the is-a test perfectly applies here. A checking account is an account, hence we make checking account subclass of bank account. A savings account is a bank account, hence we make savings account a subclass of bank account. The subclasses each have their own characteristics. For checking account, insufficient funds, process check and withdrawal. And savings account also has its own characteristics, such as annual interest rate, deposit monthly interest, and withdrawal. Besides their own characteristics, these subclasses also inherit the characteristics of the superclass, in this case bank account. And the subclasses basically not only inherit the characteristics of the superclass, but also the associations of the superclass. Besides generalization and specialization, also aggregation is supported in the UML model. Remember, aggregation was also a construct that was available to us in the EER model. It allowed us to group entity types together with their relationship types into a composite object. Well, here also we can define composite objects composed using part objects. Basically, two types of aggregation are supported here in UML. The first one is a composite aggregation, and the second one is a shared aggregation. In a composite aggregation, a part object can only belong to one composite. Right? So it's a very tight coupling. If you remove the composite, then the part object will be removed as well. So the maximum cardinality at the composite site is 1. A part object always belongs to the same composite. In a shared aggregation, as the name suggests, a part object can at the same time belong to multiple composite objects. That means that the maximum cardinality at the composite site is undetermined. It's n, right? Undetermined means n. So that means if we remove the composite object, that when you have a shared aggregation, the part object will still remain, will still exist. Here you can see two examples of that. We have a shared aggregation, employee, company. So a company can have 0 to n employees, and an employee, a company, can be considered here as an aggregation of employees. Here you can see that the diamond is unfilled. An unfilled diamond refers to a shared aggregation. In this setting, this means that an employee can simultaneously work for various companies. In the below setting, we have a composite aggregation. A composite aggregation is indicated by means of a filled diamond. So a bank is composed out of accounts. An account only belongs to one particular bank. There's a strong coupling, a tight coupling between bank and account. In other words, it means if a bank object is removed, then all connected account objects will also be removed. It's a composite aggregation, remember. Here you can see an example of shared and composite aggregations mixed in one class diagram. So we have an address book, which is made up out of contact groups. It's made up out of contact groups by using a composite aggregation. Remember, the filled diamond refers to the composite aggregation. A contact group is made up out of contacts according to a shared aggregation. An address book is made up out of contacts according to a composite aggregation. So in other words, an address book is made up out of a multiplicity of contacts and contact groups. A contact group is a virtual grouping of contacts. A contact may be included in more than one contact group. That's because of the shared aggregation, which you can see because of the unfilled diamond. So if you delete an address book, all the contacts and contact groups will be deleted too. However, if you delete a contact group, no contacts will be deleted. So you can see again whether you want to model something using a shared or composite aggregation will highly depend upon your business setting. Here you can see our personnel administration now modeled using a UML diagram. And you can see in the UML diagram that we have made use of various UML constructs. You will see a shared aggregation, you see a couple of shared aggregations. You also see that every class now has procedures or methods added. Let's zoom into a little bit more detail into this UML class diagram. First, if you look at employee, you can see that employee has various characteristics such as name, social security number, birth date, and so on. These are the characteristics, and you can see, for example, that name in our particular case is a composite attribute. It is modeled as what we call a structured domain. Name can, in other words, be decomposed into first name, middle initial, and last name. It takes on values from the name domain. Also important is that we have a weak entity type dependent, which is a dependent from a particular employee. This could be a kid, this could be a spouse, right? Husband or wife, or a child. Here we have modeled that using a qualified association, whereby the qualifier in our particular case is dependent. Note that we also again have the recursive association, which models hierarchical responsibilities of employees. An employee works for one department. The department can have at least 4, but most likely more employees working in it. So you can see we have an example of a reflexive association to model hierarchical responsibilities of employees. We have a qualified association to model the weak entity type dependent, and we also have a domain that we have used to actually define the name attribute. Some further information you can see here. Remember, in the ER model, we could model multi-valued attribute types. In our particular case, a department can have multiple locations. So instead of modeling this as a multi-valued attribute type, what we did here is we modeled it as a separate class and an aggregation in between. So in UML, location is modeled as a separate class and is related to department. So note the similarity between ER and UML. So in ER, we have an entity type. In UML, this is what we refer to as a class. In ER, we have an entity. In UML, this is an object. Attribute is the same in both cases. In UML, we have operations. We do not have operations in ER. ER only focuses on the data characteristics. In ER, we have relationship type, which is an association in UML. Relationship instance, which is a link, relationship attribute, which is a link attribute in UML. In ER, we refer to the cardinality of a relationship type. In UML, we'll refer to this as the multiplicity. In ER, we have a recursive relationship. In UML, a reflexive association. In UML, we can add a direction to the association. Remember that the direction specifies how the association will be navigated. Unidirectional or bidirectional. We don't have that option in ER. In ER, we have weak entity types, which in UML are modeled using qualified associations. In ER, we have a partial key, which in UML we refer to as a discriminator. Not many structural limitations are available in UML model. In fact, using all kinds of add-on constructs, you can even model more semantics in UML. One of them is a changeability property. This will specify the operations which are allowed on the links defined by an association. The default changeability property is allow any type of edit, but you can also specify the changeability property as add-on, which means that only additional links can be added, no deletions are tolerated. You can also qualify the changeability property as frozen, which means that once the link is established, no further changes or movements are allowed. Here you can see, for example, that we have an association between contract and vendor, which is called binds, and we have added the qualifier frozen to it, which means that the link between a vendor and contract cannot be changed after creation and is in other words frozen. UML also allows to specify constraints to links to ensure integrity throughout an object's lifecycle. Here you can see an example of that. We can specify that the objects in a group need to be ordered in a particular way by adding the ordered qualifier. We can also add any types of self-defined constraints. So here you can see that a venue hosts a number of events, and the list of events needs to be ordered. The maximum cost of any event associated with a venue should be below 100,000, and you can see that this is also clearly specified in our UML diagram. Dependency is another relationship or another type of association which can be perfectly modeled in UML. Here you're going to state that a change in the specification of a thing, that could be a class, but actually in UML, you can also have dependencies between other modeling constructs, which we haven't discussed in this session. But a dependency is a relationship that states that a change in the specification of a thing may affect another thing that uses it. So one thing depends upon another, like buyer depends upon supplier. Temporal aspects can also be modeled using the idea of a stereotype. Here you can see a history stereotype, for example, being employed to further qualify the relation between person and company. A person may work for a single company at one time. However, over time, a person may work for several companies. We hereby conclude this section on the unified modeling language.